Hello everyone, good evening. Am I audible?
Good evening, sir. Please, audible.
Okay, thank you. So, welcome everyone. This is the week 3 of the course NPTEL course Ring Theory. So, I will be taking this tutorial session. I'll explain some sample problems which will help you solve the current assignment and understand the concept better. Okay, so let's start. In last week, I have asked one. Yes, Ashok, you want to say something?
Oh, sorry, sir. Nothing.
Last week I have given one exercise which was to prove first thing is every proper ideal is contained in a maximal ideal, and then I've asked something regarding local ring. So I'll explain this now. Uh, if anyone has solved these things, they can explain. Yeah, anyone has solved? This was the proposition. Every proper ideal is contained in the maximal ideal. I'll write it here again. So most of the time ring uh, the ring which we are considering in the questions will be a ring with unity. Okay, it's a commuter ring with unity. So I will not mention it explicitly every time, but okay. So let R be ring with unity, then every proper ideal of R is contained in a maximal ideal. Okay, let's see the proof. So suppose I be a proper ideal, now consider S to be the set of all ideals J. These are also proper ideal. J is an ideal and I is properly contained in J. Okay, so we know that okay, we don't need the properly contained. J is just an ideal which contains J, which contains I. So what we know is S is non-empty. Why? Since your element I is already belongs to S, right? And S can be ordered, not, I mean partially ordered. So it won't be a complete order. Partially ordered by set inclusions. That is, I can say if J1 comma J2 belongs to A S, I'll define the order as J1 is, let's say, I mean, less equal J2 if and only if J1 is contained in J2. Okay, so this defines a partial order on this set script S. So, what do you know about John's lemma? This I will use John's lemma in this proof heavily. Is everyone familiar with John's lemma? Yes. If even anybody doesn't know John's lemma, let me know. I'll recall.
Recall, sir.
Okay. So what John's lemma says is, suppose you have a poset. Let's say, what should I name it? A. Okay. A less equal. Okay. B a partially ordered set. Okay, we call it as poset. Huh? That means A is a non-empty set with this is a partial order relation. Okay, and as a partial order is just a relation which is reflexive, antisymmetric, and transitive. Okay, so these three properties with the relation is called as partial order relation, and then you define such a relation on a non-empty set. Then that set together with that order is called as a poset, partial ordered set. And suppose for any ascending chain C, okay, subset of A. What do you mean by that? What do you mean by ascending chain? See, this is because this is a partial order. Not every two element need not have uh, every two element need not be compared. Okay, right? So this is not true that A is less equal B always or B is less equal A. This is not always true. But in a chain, you have this property that any two elements can be comparable. Okay, so suppose you have an ascending chain, or I mean, you can take instead of ascending chain, you can take for any totally ordered subset. Okay, so A is a partially ordered set with the property that any totally ordered subset has an upper bound. Okay, then A has maximal element. This is John's lemma. Okay, so now this maximal element and totally ordered subset, these are very basic set theoretical properties. Okay, you refer this to any books. This maximal element is basically an element above which there are no elements. Yeah, that's the thing. That's the only definition about for maximal elements. Just a minute. Yeah. So this is the John's lemma basically. So I'll use the John's lemma. The set scripts that are defined here, you can see it is a poset because it's a non-empty set, and I have given a partial order by set inclusions. Okay. Now if I consider an ascending chain in this script test, then the claim is if I call this element J, which is union of all elements A, where A belongs to this script C. Okay? C is an ascending chain, so that every elements are comparable. In fact, one is less equal, A is less equal B, something like this. Okay, A belongs to C. So consider ascending chain C in S. Then J. Okay, claim is that is an upper bound of C. So when do I say J is an element of C? It has to be an element of S basically. So S is set of all ideals containing I. Okay, set of all proper ideals. Set of all proper ideals containing I. So claim 1 will be J is a J is an ideal, proper ideal. Okay. Does it contains I? See, as you know, A belongs to C, which is a subset of S, and S is a property that every element of S contains I, which implies I is a subset of A for all A belongs to script C, which implies I is there in the union. Okay, so this J that we just defined is an element which contains I. Okay, that is already done. Now we just have to show that J is a proper ideal. Okay, then we will get that J is an upper bound of C. So let A comma B, two elements of J, which was union of all A belongs to C. Now since it is a union, that means A will belongs to some, let's say A, and B will belongs to some B, where A comma B are the elements in script C. Because it's an ascending chain, totally ordered, you have either A subset of B or B subset of A. Okay, these two are the only possibilities. That's the meaning of total order. Okay, any two elements are comparable. In either of the case, what we have is A minus B will again belongs to J, right? Suppose if A is contained in B, yeah, I'll just give one short description. If A is contained in B, then what do you get? Since A was an element of A comma B both are elements of B, and B is an ideal, which implies A minus B belongs to B, but J is just a union of all those B's. So A minus B belongs to J. Okay, so this is just one condition. Okay. So in either of the case, A minus B is an element of J. So I started with two elements in J. I got the subtraction in J. So that means J is a subgroup in one sense now. Now I have to verify for let R belongs to your ring R and A belongs to J. Now what happens? Which implies A belongs to, let's say, some A, or some A belongs to C. So what about RA? Since this A is an ideal, RA again belongs to A, which is a subset of J, which implies RA belongs to J. Yeah, that means J is an ideal. Okay. So we have proved that J contains I, and J is an ideal. The only step to remain to show is that J is a proper ideal. Okay. Suppose not. That is, suppose J is the whole ring R. That means 1 belongs to J. Correct? But J is the union of all ideals A belongs to C, right? Which implies 1 belongs to A for some A belongs to script C. But this is a contradiction. This is a symbol for contradiction. Why is this a contradiction? Because script C, is a collection of all ideals of all proper ideals which contains I, right? So if one belongs to some ideal, then that ideal will be the whole ring R, right? Contradiction, since A was a proper ideal. Okay, so what do we got? That implies J is a proper ideal. And J is an upper bound of C. So I'll just repeat again. We formed a partial ordered subset S. We take a total ordered set C in S, and then we showed that J it has an upper bound. That means every a totally ordered set has an upper bound. Hence, by John's lemma, the script S that we created here, this has a maximal element, right? Hence, by John's lemma, script S has a maximal element. So that will be a maximal ideal. That will be a maximal ideal containing I, because that's the property of S, set of all ideals containing I, and you have a maximal ideal in S. Okay, so this is the proposition. Heavily John's lemma is heavily used, but if you analyze what John's lemma is, then it's not a difficult thing to do. So if you have any doubt, you can ask. Anybody has any doubt? Yeah, if you have doubt, you can say. I'll repeat. If no doubt, I'll go ahead.
No, sir.
Okay. Now, using this result, this proposition that we just proved, we'll answer the next question. Question: let R be the ring with unity, of course, such that R has a unique maximal ideal, ideal M. Then show that for any element, let's say X, which belongs to R minus M, that is in M complement, X is a unit. Okay. So you can try this. You can use this result that we just proved, that any proper ideal is contained in a maximal ideal. Okay. I'll just give maybe 1 or 2 minutes. You can think. It's a very easy consequence of the previous result that we just saw. So what you have to prove, you consider any element which is in M complement. You have to show X is a unit. Okay. I'll just give a hint here. What is this? This is ideal generated by X. Right? Okay, anybody has any hints how to do it? Okay, I'll tell. So what you have to show that every element in the M complement is a unit, right? So it is enough to show that the ideal generated by that element is the whole ring R. So suppose X belongs to R minus M. Okay, let's start with an element. Let X belongs to R minus M. So consider I, which is ideal generated by X. Okay, if I is the whole ring R, then we are done, because then X will be a unit. If I is properly contained in R, then we know that by just previous result, every proper ideal is contained in a maximal ideal, right? Then I is contained in M. Why? Because you have only one maximal ideal here, right? You have the unique maximal ideal. That's the property. That means I has to be contained in M, right? Which implies X belongs to M. But this is a contradiction, right? We took X in M complement, then we were saying that X belongs to M. This is a contradiction. Hence the second case is not possible, hence I has to be equals to R, which implies X is unit. Okay, so this property of a ring having only a unique maximal ideal, this is called a local ring. Okay, a ring such that which has a unique maximal ideal is called as local ring. Well, just right here. A ring which has unique maximal ideal. So this property in fact characterizes local ring. Okay. So the next thing what I want to say is converse. Conversely, suppose I, which is collection of all x belongs to R such that x is a non-unit, forms an ideal in R, then R is a local ring with unique maximal ideal I. How can I prove this? What do we know that I forms an ideal, right? So suppose you take I is contained in M is contained in R, where M is an ideal. Let is properly contained in M, which implies there exists an element X belongs to M minus I, right? But what is I? I has all non-units. That means every element which are not in I is a unit, right? Which implies X is a unit. And you know that if an ideal has a unit, then the ideal has to be the whole ring, which implies M is whole R. Which implies what? I is maximal. Now I want to show it's a unique maximal ideal. That means, suppose I don't have to show actually. Let any I, not I, no, I is already there. Let any I tilde be an ideal such that I tilde is not equals to I, right? That means there exists an element, right, which is not there in I, x naught which belongs to I hat, but x naught is not in I. But if not in I, that means it is a unit, which implies x naught is a unit. And this is enough to claim I hat is the whole ring R. That means it cannot be a maximal ideal. So, you don't have any ideal which in fact which is other than I. Proper ideal. So this is the characterization of local rings. You have any doubt? Just give me 1 minute. Okay. If no doubt, we'll go for the next question. Which is let phi from R to S be a homomorphism of commutative rings. Then A, prove that phi inverse of P is an ideal of R whenever P is an ideal of S. Yeah, okay, by the way, uh, when ideal is defined only on proper subset, right? I mean, the whole ring R can be considered as an ideal or not? Can anyone tell me how Sir defined an ideal? Because different people define it in different way. So the question that I'm asking is, when I say I is an ideal of R, does this imply I is a proper subset of R? Because if not, then we have to make some changes in A, question A. I mean this. Okay, I hope this is proper only. Then the change is prove that phi inverse of P is equals to R or phi inverse of P is an ideal of R. Okay, these are the these conditions. And in B is you have to show if M is a maximal ideal and phi is surjective, then phi inverse M is also a maximal ideal. Okay, surjectivity is important here. You can find an example where it doesn't work. So proof. Phi be a homomorphism of commutative rings Okay. Let P be an ideal I'll call I as phi inverse of P. Okay, so I want to show that I is again an ideal. So take any two elements, like A comma B belongs to I. So what happens for A minus B? Hmm? So phi of A minus B is same as phi of A minus phi of B. Since these two elements belongs to P, P is an ideal, this again belongs to P. And for any R belongs to ring R, what happens to phi of RA, which is phi of R times phi of A. And since phi A belongs to P, P is an ideal, this again is in P. That means RA belongs to phi inverse P. And here it implies A minus B belongs to phi inverse P. So this implies phi inverse P is an ideal. Okay. So part B. Uh, what do you have? Let is a maximal ideal. I want to show that phi inverse of M is also maximal ideal. So I know that phi inverse of M is an ideal by A. So suppose phi inverse of M is contained in another ideal I. Okay. Let's say it properly contains. I have to show that I equals to R. What happens to phi of I? Phi of I set of all phi x, where x belongs to I. Okay. Claim is this phi I will again be an ideal. So take any two elements x comma y belongs to let a comma b belongs to phi of I. So what is a plus b? A is equals to of course phi x and b is equals to let's say phi y, which implies a plus b is equals to phi of x plus y by homomorphism, which implies ab again belongs to phi I. And similarly for any r belongs to s, you take ra. Ra is same as r times phi x. Okay, but now because you have surjective math, r can be written as phi of some r dash. Okay, and this phi x. So this is phi of r dash x, which belongs to phi I. Okay, so what I want to say basically is phi I will be an ideal from this statement. Now since m this phi inverse of m is in I, what do we get is M is contained in phi I. Okay, but M was a maximal ideal, which implies phi of I has to be whole R, right? But when is this true? Because phi is subjective, right? I has to be the whole ring R, correct? Right. So what do you have? I'll just write it here until what we have proved. We have proved that if if phi inverse of M is contained in I, then M is of course contained in phi of I, which is an ideal, which is equals to whole ring R. Okay. So what can I conclude? Is this possible? So since phi inverse of M is properly contained in M, which implies okay, what does this imply? Phi is surjective and not injective. Can we say this? So if M is an ideal which is contained in an ideal I properly, and you take an element x naught which is outside M in I, can I say phi x naught is not there in phi of M? Suppose.
Okay, sir.
Yeah, yes, yes. What do I say?
Okay.
No, no, I'm asking. Suppose we can say, then I can write like this. Yeah. So M belongs to capital M. Then this will imply phi of x naught minus M is what, 0, right? So which implies x naught minus M belongs to kernel phi, which is also an ideal. What I can say. Suppose this is like some I1. I have some confusion regarding this. Okay, let's keep this question right now. I'll see what confusion I have. Let's go to the next question. Next question is about Boolean rings. Okay, so you have the ring R. Everywhere R is a ring with unity. R is called a Boolean ring if A squared equals to A for all A belongs to R. Okay, this is the thing. The question is, prove that every prime ideal of Boolean ring is maximal. Okay, so let I be a prime ideal. So consider R quotient I. What is this? This is A plus I, where A belongs to R. Okay. The question is this R plus R quotient I is again a Boolean ring? So let's take two elements, A plus I and B plus I, or let's just take any element and do the product. You know this is A square plus I, right? But A square is A. Right? This is A plus I. So product of an element with itself is itself again, right? That implies R quotient I is a is also a Boolean ring. But now you have R quotient I is also an integral domain, right? Since I is prime ideal, you have R quotient I is an integral domain. So what do you have? In an integral domain, if you have x squared equals to x, then what do you have? X times x minus 1 is 0, right? This implies x equals to either 0 or x equals to 1. Right? So you have only two elements in an Boolean ring which is an integral domain. Right? That means this is a field, right?
Yes, sir.
So our quotient I is just something like 0 bar 1 bar, which is a field. Hence, I is maximal ideal. Okay? So this is about Boolean ring. So see you can see the Boolean ring is all characterized by only one property, that a square equals to a. Huh? So what is special about taking squares? Hmm? So if I say that for any element a there exists a natural number n such that a power n is equals to a, then can I say the same statement that every prime ideal is a Boolean? Every prime ideal is a maximal ideal. So the answer is yes. So that will be proven next. That R, I mean, the same assumptions are there with R, ring with unity, commutative ring with unity. Let uh, there exist n belongs to natural number, right? For any a belongs to R, there exists n belongs to natural number which depends on a, such that a power n is equals to a. Okay, this is the property of the ring now. Then prove that every prime ideal is maximal. Proof. Again the same thing. Consider first of all, let I be a prime ideal. Now consider R quotient I. Since I is a prime ideal, R quotient I will be an integral domain. So does this R quotient I also have the same property? That's the question. So take any element A plus I and multiply it n times. So you know what is the multiplication? It is A power n plus I. But you know this is A plus I because the ring property. That means R quotient I again has the same property. So, but R quotient I is an integral domain, right? So if x belongs to some, so what I'm using is, if R is an integral domain and x power n equals to x, then what do you have? X raised to n minus x equals to 0, which implies x times x raised to n minus 1 is 0, which implies either x equals to 0 or x raised to n minus 1 is 1. That is, x raised to n minus 2 times x is 1, right? So what do you get from here? Either x is 0 or x is a unit, right? X has a multiplicative inverse. X times something is 1. That means in an integral domain, if you have this property that x raised to n is x raised to n equals to x for some integer n, then x is either 0 or x is a unit, right? That means every non-zero element is a unit, right? So I can say, which implies every non-zero element of R, not R quotient I is a unit. Hence, R quotient I is a field, which implies I is maximal ideal. Okay, so you have any doubt in this?
No, sir.
Okay, we have proved that for any ring with the property that a power n equals to a, every prime ideal is a maximal ideal. Let's go for the next question. So consider the ring of continuous functions now. So set of all functions from 0, 1 that are continuous. The another notation for this set is C01. Okay. So consider this is the ring with pointwise addition and multiplication, pointwise multiplication. This forms a ring. So for each C belongs to 0, 1, define the set as IC, which is set of all functions such that if C is 0. All functions which vanishes at point 0. Okay. Then prove that first thing, that IC is maximal ideal of R for each C in 0, 1. B, for any maximal ideal M, there exists C belongs to 0, 1 such that M equals to IC. So what does it say? First thing is IC is a maximal ideal, and second thing is any maximal ideal is of this type. Okay, so these are interesting question. So you can characterize all maximal ideals in this ring of all continuous functions on compact Hausdorff space. Yeah, cool. So let's prove part A. what you want to show that IC is maximal ideal, right? Clean. So consider R quotient IC. Just 1 minute. R quotient IC is set of all F plus IC, right? F belongs to your ring R. So let F plus IC is a non-zero element in R quotient IC. What does this imply? This implies F doesn't belongs to IC. That is, F at point C is non-zero. Okay. What I have to do is I have to give a multiplicative inverse for this element F plus IC, right? Then I can say that R quotient IC is a field, hence IC is a maximal ideal. Okay. So define G from where? From 0, 1 to R as G of X is equals to 1 upon F at C for all X belongs to 0, 1. Okay. So I define a constant function basically which value 1 by Fc, well defined because Fc is non-zero. Then what happens to Fg? Fg at point C is 1, right? So this is basically F at C times 1 by F at C, which implies Fg minus the constant 1 function belongs to IC, right? Which means Fg plus IC is same as constant 1 function plus IC, right? So this means F plus IC times G plus IC is equals to unity in the quotient ring, right? This means F plus IC has a multiplicative inverse, right? That means every non-zero element has a multiplicative inverse, which implies this quotient ring is a field, hence IC is a maximal ideal. Okay, in doubt? Okay, if no doubt, go to go for part B. Now what I have to do is I have to show every maximal ideal is of this type. So I have to find. Let's consider a maximal ideal. Uh, 1 minute. Okay. So for part B, let M be a maximal ideal of R such that M is not equals to IC for any C belongs to 0 volt. What does this imply? This implies for each C in 0, 1, there exists a function fc belongs to M such that fc at point C is non-zero. Right? That's the definition of M not being equal to IC. But since fc is a continuous function, there exists open neighborhood VC of C such that f at x is non-zero for all x belongs to VC, right? And you know that the whole closed 0, 1 is contained in union of all those VC, right? It covers. Now, but since this closed 0, 1 is compact, it can be covered by finitely many such open sets. Is union simply VC1 union VC2 up till union VCN, let's say. Now define function g as g of an element x equals to fc1 x whole squared plus fc2 at x squared until fcn x squared. Now since fci's were in ideal M, their squares are in M, their summation is in M. That means this is which implies G is an element in M such that G I mean the claim I was about to say is G is G is non-zero at every point. Okay, so basically take any point x belongs to 0, 1, x belongs to VCI for some I. That means FCI at x is non-zero, which implies G at that x, which equals to, see, what will be Gx? Gx will be sum of these entries, right? And for some I, this, let's say 2, FC2 at x is non-zero. That means the whole Gx will be non-zero, right? Because there are squares and sum, right? It is 0 if and only if each term is 0. But I have one term which is non-zero. This will guarantee that Gx is non-zero. Hence I am done, which implies G is a unit and M is an ideal, hence M was the whole ring R. This is a contradiction. Because M is a maximal ideal, right? A maximal ideal cannot be the whole ring R. Hence, M has to be equal to some IC or some C belongs to 0. Okay, any doubt?
No, sir.
Okay, so let's go for the next question. Now see, there is an importance of closed 0, 1 here, the compactness. Okay, so if you don't have compactness, you don't have this result that every maximal ideal is of this type. Yeah, the next is a counter example for the same thing. Now consider R to be set of all functions which are continuous, but the real valued and the domain is also R. Okay. Now and I will be the collection of all functions such that which has compact support. What does this mean? That is, there exists I is compact and F fx equals to 0 for all x belongs to I complement. Okay, this is the definition of f having compact support. Okay, this is I. So what you have to show is, first, I is an ideal. It is not prime. Okay. I is a subring, of course. If you take two functions, let f comma g belongs to I, and yeah, so I is confusing. I'll write here what, m s s. So there exists s1 comma s2 subset of R such that s1 comma s2 are compact and fx equals to 0 for every x belongs to s1 complement and gx equals to 0 for all x belongs to s2 complement. Okay. So what do you have? Claim is that f minus g should also belong, right? So if I take x is in s1 complement intersection s2 complement, this implies f minus g at x is 0, right? But what is this? This s1 complement intersection s2 complement is s1 union s2 whole complement, right? So since s1 and s2 are compact sets, does it guarantee that s1 union s2 is also compact? So yes, because S1 and S2 are subsets of R and they are compact if and only if closed and bounded. Since S1 is bounded, S2 is bounded, union is bounded, and finite union of closed set is closed, and S1 union S2 is closed. This will imply S1 union S2 is compact and f minus g at x equals to 0 for all x belongs to S1 union S2's complement, hence f minus g is in I. Now take any h belongs to R and f belongs to I. What happens to hf at x? Which is hx times fx. So if x belongs to let's say support of f, okay, this is another notion, but this is not good. Not support, I want the other part. Okay, so if x belongs to the s, which s1 let's say, which implies fx is 0, which implies hf at x is also 0, right? So again, hf belongs to I. So what did I show? That set of all functions with compact support is an ideal. Okay, I have to show it is not a prime ideal. So this is very easy. It has a 0 divisors. Basically 0 is there, right? 0 belongs to that ideal. 0 belongs to I. Consider these two functions. One which goes 0 here and here, this like this. Another which goes like a line until here and then 0 here. Right? So if you consider these two functions, so let's label this as f and this as g. And what do we get? F dot g belongs to I, but neither of them belongs to I. right? Because no one has compact support, right? Because they are going to zero, they are not going zero at x goes to infinity, which implies I is not prime. Now, if we appeal for the appeal for the question that we just asked before this question, we have proved that every maximal ideal is of this type. So I'm claiming that this ideal I is of course this ideal will be contained in some maximal ideal. The claim is that maximal ideal is not of this type. Okay. So how do I write it nicely? Would be that I is contained in M, where M is a maximal ideal. This is always true. We have already showed that every proper ideal is contained in the maximal ideal. Maximal ideal. Then show that M is not equals to IC for any C belongs to R. Okay. So how do I show this? So what is IC? I'll just recall again. IC was set of all functions which vanishes at C, right? Right? But M contains I, right? So I can define let C belongs to R. What I'll do is I'll define a function visually. If you want to see, you take any element C here. What I'll do is I'll take a constant function until the point minus C to C closed, and then you take minus C plus 1 here, so minus C minus 1, C plus 1 here, and you decrease it down to 0, right? And then go beyond there, everywhere 0. Okay, this is a well-defined function, right? This is my element H, let's say. So what do I have is this element H has a compact support, of course, because it's 0 after C plus 1, okay? So H belongs to I, but H does not belongs to IC. This I can do for any real number, any real number C, right? Which implies M is not equals to IC. Basically not contained, because I was contained in M, right? So there exists a maximal ideal which is not of this type IC. And why is this happening? Because here the ring is of C is on C over R, right? Remember, this is a set of all functions from R to R, not 0 1 to R. That is the very crucial property. 0 1 was a compact set, whereas this R is not compact. Right? Hence, there are maximal ideals which are not of the type IC. Okay. I hope you understand this. Is there any doubt?
No, sir.
Okay. Okay. So if there are no doubts, then today's session will be over. My health is not good, so I'm not able to take further session. I'm sorry for less hours. It will be just 1 hour, 10 minutes
It's
session.
okay, sir. It's okay.
Okay. Okay. Thank you then.
Thank you, sir. Thank you.